So here is our review of chapters 3 and 4. So chapter 3 was two-dimensional motion, and there'll be one problem on the test involving two-dimensional motion, at least just from that. Well, yeah, it'll just be one problem. So basically what we have is some situation where an object has some initial velocity v0 of some value. So I'm not going to tell you what it is. And then you have this angle relative to the horizontal. So the whole idea of two-dimensional motion is to break it up into two components. And we always break it up into an x and y component. And most of the time we're dealing with x being the horizontal and y being the vertical. Now in chapter 4 we have motion up and down flat ramps. And in that case we align the directions parallel and perpendicular to the ramp. But for projectile problems, typically the y direction is the one that's under the influence of gravity, and the x direction is the one that doesn't have any forces acting on it. So the vector part of two-dimensional motion is we break up the initial velocity into two components. So we take the magnitude of the initial velocity, and because the velocity triangle looks like this, where this is v0 and this is v0y and this is v0x, and this is the angle from trigonometry, v0x is going to be v0 cosine of the theta angle, the angle that it's shot at, and v0y is v0 sine theta. And typically theta is some number between 0 and 90 degrees. Okay, so then you have the components of the velocity. So we have the x components, and for the x components it is a constant velocity situation. Which means the x direction acceleration is 0 meters per second. And what falls out of the whole thing is that the change in x position, or the x displacement, is equal to the x component of velocity times the time. So this is the x component, the initial x component of velocity. And after some period of time, it's going to have traveled a certain distance, and that's, linear, a linear equation in t. And then we have the y component. Now that is constant acceleration. So a sub y is, given the way that we have defined our coordinate system, is negative 9.8 or 9.81 meters per second squared. Now for that particular direction, we have the four equations. Delta y is equal to v0y plus vy divided by 2 times t. Then we have the v0 or vy. V sub y is equal to v0y plus a sub y t. Delta y equals v0y t plus 1/2 a sub y t squared. And v sub y squared is equal to v0y squared plus 2a sub y delta y. So those are four equations which apply to constant acceleration situations. So remember, time connects the x and y directions. So that is, typically you can maybe you're given enough information to calculate t from the x component. That would be the case if you had like a vertical wall that you'd shoot something up and it would hit the vertical wall. So that would specify delta x, and from delta x and the initial x component velocity you get the time, and then you could use the time to find out how much change in y dimension there is. Or the case of the y situation is you have something's going out and it's going to be limited by how far the thing falls. And remember, in these cases, this delta y is negative because typically you shoot something, it doesn't have to be. I mean, I could have, if I did this, let's say, this is another scenario. Let's say I shot this thing off, and this way it goes up like that. So this is delta y. In this case, delta y is positive. So you just gotta draw the thing and see what's going on. But say this, either one of these two scenarios, shooting up, shooting it down. What you're going to do is you're going to use these equations to solve for the time it takes to hit the ground, or to hit the ground higher here. And with that time, you can then calculate how far it's going to move in the x direction by using that time and the x component of velocity multiplied together to give you the delta x. And what I'm going to do is I'm going to give you, it's going to be pretty straightforward. I'll give you some initial velocity at some angle. You break it up into the two components. If there's a vertical surface, then you'll use this equation to solve for t. If it's a horizontal surface that it's going to hit, then I use this one to solve for t. And whichever one I don't use to solve for t, so in this case I'd use the t solved and then use this equation to solve for delta x. If it's this scenario, then I'd use the t calculated here to use it in there. And using these equations are just like we used in chapter 2. Okay, so that's the projectile problems and the equations that would apply and the values that you would use. The next one is this equilibrium problem, and it's going to be very similar to what was in the class. We have some object that's being hung. Let's say this is 1, 2, and 3 as far as the lines, and the whole idea is to break this up into components. So this is the physical drawing, but if I had the actual drawing, it would probably look something like this as far as the free body diagram. And this would be F1, and this would be F2, this would be F3, and this would be theta 3, this would be theta 2, this would be theta 1. Obviously theta 1 is equal to 270 degrees. And you can, what I'll do is I'll give you these angles. So those are not, this would be theta 3, but this one is not theta 2. Theta 2 is the angle from the positive x-axis over here. And what we do is we, in this case, we break the force up into the components. So you're going to calculate, and I'm not going to do it all for you, I'm just going to lay it out here. So, F1x, the x component of force 1, actually in this case is 0 because it's vertical, and F1y is going to be F1 times the cosine or sine 270 degrees. going to be negative 1. Sine of 270 is negative 1. So you get negative f, whatever f1 is, because that's going to be pushing downward. We're going to use this same coordinate system, x horizontal, y positive, y vertical. And then, you can do the other ones. F2 is f2x is f2. Now, which one is it? Is it the cosine or the sine? Well, again, if you take this force and you break it into two components, you're going to have f2y and f2x. This is the adjacent side relative to this angle, so it's going to be the cosine of theta 3, and f2y is going to be equal to f2 times the sine of theta 2, and the same thing for f3. And if you use the angle from the positive x-axis, you'll get the correct signs. You'll get a negative component, x component, and a positive y component. And I've actually drawn this to try to be more accurate, because what we find out is that the x components balance each other out. There's two forces that have x components, F2 and F3, and so the x components have to be equal to each other, because ultimately, so I'm going to let you fill that out in your formula sheet. So this is F3y. Okay, it's equal to something. Now, as far as equilibrium, equilibrium is when there's no motion, I guess I could say no acceleration, which 99% of the time means v is 0 meters per second, meaning it's not moving at all, even though these equations would apply if it was moving at a constant velocity. And as a consequence, you end up with these two equations. The sum of the forces in the x equals 0 newtons, and the sum of the forces in the y direction equals 0 newtons. And if you go back to the homework problem that we worked in class that you handed in, we had a couple of different scenarios. We had where I gave you the mass here, and you could calculate the weight, and then the weight would be equal to the tension in this cable. So basically giving you F1, and you have to calculate F2 and F3 by solving two simultaneous equations. So go back and look at that. Hopefully you did a good job. I'm not going to work through it out completely again, but just giving you a kind of feel for what kind of problem will be on this relative to the equilibrium. So what I would suggest is you go back and you look at your notes. We did 3 scenarios. I'm not going to do the one where you have to solve for the unknown angles. I'm going to give you the angles. So I'm either going to give you the mass, and that means you have force 1, or I'm going to give you one of these forces, and then you have to calculate the other 2 forces. So as long as you understand those problems, so it means you got to go back and look at them and not just write them down. If you just write them down, you're going to get to the test and you're not going to know what the heck is going on. So I just want you to spend some time analyzing those problems to completely understand them. Okay, so there'll be one problem like that. And then there'll be 3 problems involving Newton's laws and motion, and we went through quite a few problems associated with that. So you've got, something, there's 2 cases here with just a straight surface. So we could have something moving along horizontally at some initial velocity, say v0 is equal to 4 meters per second. And we want to do the free body diagram, so make sure you know how to do free body diagrams. So for example, if I drew a free body diagram here, and you can work out the details, you're going to have the friction force pushing that way, you're going to have the weight going down, and you're going to have the normal force going up. And so that's what I'm looking for this situation. Now, if you were doing something on an incline, And this is, you could be sliding up the incline, you could be sliding down the incline. It'll be a sliding situation. We won't just have it sit there. So let's say it's sliding up the incline, some value, 4 meters per second. So if we looked at the free body diagram for this scenario, and what we would do is break it up into x and y components, where x is parallel to the surface and y is perpendicular to the surface. And what our free body diagram would look like there is you'd have the weight going down, you'd have the normal force pushing up like that, and you'd have the friction force going this way. Okay. So this is your friction force. And of course what you do is you take that weight and you break it up into two components. So you'd have W sub y and you'd have W sub x going this way, W sub x, and you'd get rid of W. So when it's sliding up the ramp, it's slowing down because of the friction force, and it's also slowing down because of the x component of the weight. Now if it was frictionless, you wouldn't have the friction force. Now in all of these cases where you have friction, you have this relationship between the friction force and the normal force, like that. In the case of an inclined plane, the normal force is going to be, again, is going to be equal to the weight. So let's just do the free body diagram, or the Newton's laws for this particular problem. So when you have a scenario like this, you have in the x direction there is movement, so there is an acceleration. In the y direction there is no acceleration. So this would be a sub x and this would be a sub y. So I could put a sub y, but the reason that's 0 is a sub y is equal to 0 meters per second squared. So you have one equation, and what you use this for is to relate the normal force and the y component of weight. So here's your y component of weight, here's your normal force. They have to balance out. So what you find is the normal force is equal to the y component of the weight. Also remember that the x component of the weight is the weight times the, well, let's see which one that is. Here's theta. That's the angle between this theta here is that theta. So the y component is the cosine of theta, and w sub y is, or w sub, wrong one. You gotta be careful here. So when it comes to weights, and you break it into the components, the x component is this one, which is the same as this one right here. So it's the opposite side, so that's going to be w times the sine of theta, and this one's going to be w cosine of theta. And you can tell when theta equals 0, sine of 0 is 0. So when theta is equal to 0, there should be no x component, which is what is true. So that's good. So that's how you get the components of the weight that you replace. Remember, the weight is the mass times the acceleration due to gravity. Then you break it up into the two components. So then you could, once you have the y component of the weight, you can figure out the normal force, and then you would use that normal force, this part here, to calculate the friction force. That's equal to the coefficient of friction times the normal force. So then you can calculate the friction force, which then is used in this equation. So again, we look at the free body diagram, and we see that both of them are pointing in the negative direction. So we'd put a negative friction force and a negative W sub x. And as a consequence, friction force is positive, W sub x is positive, but they're both changed signs, so these both are negative. And therefore, because mass is positive, acceleration must be negative. The product of these has to be negative to make it agree with the right-hand side. So the acceleration when you do this problem, this particular example, would be negative, which makes sense because positive acceleration would be up the ramp, which means it would be speeding up the ramp, but we know that doesn't happen. So negative acceleration would be down the ramp. Therefore, we're slowing it down as it goes up. Now, remember, once you've calculated the acceleration, you can use that calculated acceleration with constant acceleration equations, which we just wrote. So use the calculated acceleration that we would get from Newton's second law with the constant acceleration equations, which are back here, these equations. Using, if it's x, use x. If it's y, use y. In this case, we'd use x's to solve for, velocity, time, and delta x. So these problems may consist of both a Newton's second law problem and a constant acceleration problem. So be able to do both of those. Again, you can look back at the examples we went through class to make sure you understand it. Okay, now, and what I'm going to do too is I have some videos of constant acceleration examples like this. We did go over in class, and if you feel comfortable with this, that's fine, but I'm going to post that video with the different scenarios that we went through. If you didn't take very good notes, you can watch them again if you want to do it. Okay, so that's one class of problems, and there may be one or two of these where you have an object that's not interacting with another object. It's just well, it isn't. It's interacting with a surface, but not with another object. And then we have this third case, motion caused by a hanging mass. And we did that a lot in class. So there are a couple of scenarios there that we would do. You'd have some object here that's going horizontally, sliding along the surface because it's being pulled downward by this hanging mass. We'd have M1 and we'd have M2. Or we could have the case of an inclined plane again, a straight inclined, well, I guess that's redundant. Plane is straight, flat. So you'd have this scenario. And if you have the equations that I derived in class, you can't use those, okay? You're going to have to start from scratch and derive everything. So, in a case like this, most likely I would give you the two masses. I might give you, if there's friction, I'd give you a coefficient of friction. If it's frictionless, then I wouldn't. You'd have a zero coefficient of friction. But, and then you'd have to calculate the acceleration of both objects. Remember, depending upon how you define the coordinate system, if I define y positive going up here for this object, moving in the positive x direction for this mass is going to be moving in the negative y direction. And you have to relate A1x and A2y in this case. So the y movement of this thing is going to be the same value of acceleration, except for the sign maybe, as this one, because they're connected by a string. So you'll need to relate those two. They're either equal to each other or they're it's going to be a1x equals plus or minus a2y. That's what you got to figure out. Which one makes sense. You just have to look at the way the coordinate systems are defined. And then you would have, let's say for this one down here, if I drew the free body diagram for this object, you'd have the weight going down, you'd have the tension pulling up, so that's T, this is W, you'd have the normal force going that direction, and you'd have the friction force going downward if there were friction. If there were no friction, then you'd leave that out. And just like before, you're going to take this weight and you're going to break it up into two components. You're going to have W sub y, you're going to have W sub x. Get rid of that. And I could also put the W sub x over here as well. Get rid of that. Okay, so I've just moved it. I haven't changed the value, I haven't changed the direction, so it's the same thing. So if you apply the sum of the forces in the x direction, remember x we would define either going up or going down the inclined plane. So sum of the forces in the x direction or this direction, so you'd have, and it's moving in that direction, so you'd have m m1 times a1x. That's the inertia term, and then you'd have tension going up the ramp, and you'd have friction going down the ramp, and you'd have the x component of the weight going down the ramp. So this is equal to that, and then you would have in the y direction the sum of the forces equal to 0. That's because a1y equals 0. I'm just looking at this one. This is the thing that connects the two objects, is the acceleration. But I can look at each one of these separately, do a free body diagram. And then again, you're going to have that the friction force is equal to mu sub k times the normal force. So you can see from, I forgot to, let me move that down. I've got to finish this one off. So here, 0 is equal to, go over here to here, okay, y positive is going away from the surface, so that's F normal. W sub y is going into the surface, that equals 0. So you can see I can solve for W sub y, it's the normal force. Use the normal force and the coefficient to find the friction force to find that. And then, just like before, the weight is equal to the x component of the weight is W times the sine of theta, and W sub y equals W times cosine of theta, where W is just the mass times acceleration due to gravity. So you can see I can calculate W sub x from the weight and the angle, calculate W sub y from the weight and the angle, calculate the weight from the mass and the acceleration due to gravity. So in this case, I know this, check, I know that. I wouldn't know the acceleration, and I wouldn't know the tension. So what you have to do is then go to the hanging mass, and it has a free body diagram that looks like this. So you'd have the tension pulling up and the weight pulling down. And I'm going to define y positive going up. So if we apply Newton's second law in the y direction, that's equal to m2 times a2y. And we've got tension going up, and we've got W2 going down. So what we end up with is two equations. This one, where I don't know a1x and I don't know t. Here, I don't know a2y and I don't know t. I can calculate W2 from the mass. I know the mass. So the third equation you have to use is this one here. So you can just, you could call this, well, probably what I would do is I'd substitute for this, I'd substitute that. And again, you got to decide whether it's plus or minus. I'm going to let you look at that. If you have any question, if you want to ask me, I'll I'll answer you, but you're going to have to think about it first for this particular scenario. So you're going to end up with two equations, this equation and this equation. And then you can do substitution. Again, you can look at your sheet that we did in class. If you look at your sheet and you don't understand what you wrote down, ask me and I'll explain it to you. Okay. Don't just sit there and say, I don't know what he was doing there, so I'm just not going to do anything. Either ask another student who might be able to answer the question, or ask me and I'll explain what it is. But you're going to have to put some time into getting all this, how this stuff is all connected. Again, writing down the equations without understanding what's going on is just a recipe for disaster. So that is pretty much it. So there's a couple of scenarios. I could have, with or without friction. I could have sliding down instead of sliding up. This one has to slide down because there's nothing that would make it go the other way. I guess theoretically I could give you initial velocity in this direction, and this thing would slow it down ultimately and stop, and then it would pull it back the other direction. And then we've got these scenarios where we've got an object either on a flat surface or on an inclined surface. Here it could only slide one direction, but here it could, if the angle, well, no matter what the angle is, if I give it some initial velocity, it's going to slide up initially and then stop and then go backwards. If it's going down, I could give it some initial velocity and it would accelerate downward, or I could have it stationary and let go of it and it would slide down. So there are probably about 10, 12 different scenarios, but they all just involve tweaks of what we're doing here. And the whole idea is to realize what free body diagrams are, how you use Newton's second law to come up with equations relating forces and acceleration, how friction is related to the normal force through the coefficient of friction, how to break the weight up into the components when you're on an inclined plane, how you can calculate the mass as the product of the weight is a product of mass and acceleration, and the acceleration due to gravity. And also, if you then calculate an acceleration, use that acceleration with, say, a given initial velocity to calculate time, final velocity, and displacement. I'll give you one of those three because you still need 3 out of the 5. But one of the 5, acceleration, is determined using Newton's second law. And then I have to give you some initial velocity. So the third thing is something else I have to give you. I say it slides for 5 seconds. It slides until it stops. The velocity increases from something to something. How far does it slide? So there's a whole bunch of different ways that you can kind of test your knowledge here. That's not going to be an exact repeat of what I'm doing here. So again, don't feel super confident if you're like, oh yeah, I could do those 4 problems that he showed me. You have to understand the procedure and how I got there, so that if I change something slightly, that you can react to it appropriately.